Assalamualaikum, my name is Nora and Atira Bida Azmi with ID TJ24042. So today I am going to introduce Reactor Scale Up and bioprocess, which is the critical process of transferring a successful laboratory concept to a full-scale production plant. Our main objective is to ensure that as we increase the size of the operation, we maintain the exact same product quality, yield, and performance. This is vital because it enables the commercial production of life-saving products like vaccines and antibodies while reducing financial risk and time to market. However, scale-up comes with risk if handled poorly. Specifically, it becomes much harder to maintain optimal conditions like pH and temperature, ensure efficient mixing and aeration, and manage heat transfer across larger volumes. Ultimately, successful scale-up is about overcoming these physical challenges to bring lab-proven science to the masses. Moving on to the bioprocess stages, the journey begins with upstream processing, which is centered around the growth and development of cell lines or microbes through steps like cell selection, media preparation, and fermentation to maximize product extraction. Once the biological molecules are created, we move into downstream processing to separate and purify them using techniques like clarification, cell disruption, and concentration to ensure high purity and an acceptable yield. Finally, we reach product formulation and fill finish, where we perform buffer exchanges, add stabilizers, and conduct sterile filtration into vials or strings. The final stage is crucial as it ensures the product stability, shelf life, and full compliance with regulatory specifications before it reaches the consumer. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Patricia binti Zahrom and my ID number is TJ24029. So I'm going to explain about the geometrical similarity. So what is geometrical similarity? So geometrical similarity in a reactor scale-up means that the large-scale reactor is a proportional version of the laboratory or pilot-scale reactor with all the key dimensions increased by the same scale factor. The ratios of all geometric dimensions are kept constant during scale-up. For example, the tank height to diameter, impeller diameter to tank diameter, impeller clearance from the bottom to tank diameter, baffle width to tank diameter, and lastly, the number and position of impellers and baffles. So why do we need to maintain geometrical similarity? So by maintaining it, we can ensure that the flow patterns, mixing zone, and circulation behavior in the larger reactor resemble those at smaller scale. So this is important because mixing efficiency, heat transfer, and mass transfer are strongly influenced by reactor geometry. Next, I'm going to explain about the scale-up challenges. First is the mixing limitations. So at larger scale, it becomes harder to achieve uniform mixing, leading to concentration gradient, dead zones, or poor suspension of solids. Next is heat transfer constraints. So by removing or supplying heat is more difficult in large reactor. Next is mass transfer limitations. So gas liquid and liquid solid mass transfer rates often decrease with scale. So this will affecting the reaction rates, oxygen transfer, or dissolution efficiency.
Hi, my name is Nur Aida Isaswaha binti Muhammad Rosli with ID number TJ24038. I will explain about scale-up criteria. The definition of scale-up criteria is the rules used to ensure a large reactor behave the same as the small reactor by maintaining key physical and operational condition. There are some key points that need to remember, which is the first one is selection depends on microorganism and process type, whether is it aerobic, anaerobic, batch, or continuous. The second one is no single criteria can satisfy all requirements. Last but not least, trade-offs are often necessary between mixing, mass transfer, heat transfer, and shear stress. There are some examples for scale-up criteria, which is geometric similarity, dynamic similarity, mass transfer, heat transfer, last but not least, which is mixing time.
Next, this slide shows the main scale-up methods. These methods help us enlarge a reactor while keeping the same mixing, heat transfer, and mass transfer behavior as the smaller one. There are 5 key methods. The first one is constant power per volume, which keep mixing energy and turbulence similar. Second, constant tip speed, which maintains shear and is good for shear-sensitive cells. Third, constant Reynolds number to keep the same flow regime. Next, is constant Froude number, which maintains vortex behavior at the liquid surface, and lastly constant KLA, which keeps gas liquid mass transfer consistent, especially for aerobic reactors.
Assalamualaikum and a very good morning. My name is Nur Najausna binti Muhammad Zamri with ID number of TJ24045. So now I will explain about the microorganism-based scale up. So for microorganism-based scale up, it means that when we increase the reactor size, we must consider about the biological characteristic of the microorganism that we use. So different microorganisms will react differently to the physical conditions such as mixings, oxygen supply and also shear stress. Okay, for example, bacteria and yeast are generally more robust, so they can tolerate a higher agitation and also shear stress. So scale up for bacterial processes is usually much easier. A common example is E. coli for enzyme production and yeast for the ethanol fermentation. However, filamentous fungi and animal cells are much more sensitive. Filamentous fungi can be damaged by excessive mixings, which will affect their cell structure and also product formation. For animal cells, such as CHO cells that used in vaccine and antibody production, they require a very gentle mixings because they are highly shear sensitive. So therefore, during the scale up, different strategy must be used depending on the type of the microorganism to avoid the cell damage and loss of productivity. Next, I will explain about the scale down concepts. It refers to the simulation of the large scale reactor conditions by using a small scale system. Instead of directly scaling up to an industrial reactor, scale down models are used to study the problems that may occur at the large scale. So the main purpose of scale down is to investigate the non-ideal conditions such as oxygen limitation, poor mixing, and also nutrient gradients. So these conditions are common in large reactor but very difficult to study directly. So for example, a small stir tank reactor can be used to simulate the oxygen fluctuation found in the large fermenters. So by exposing microorganisms to these conditions at the laboratory scale, we can observe their response and also improve the scale up strategy. So in conclusion, scale down models helps to reduce the cost and risk, and they also increase the success of industrial scale up. That's all for me. Thank you.
So for scale up models, it is important to understand that scale up models, we are not talking about different types of physical bioreactor. Instead, there are the mathematical strategies we use to predict how a process changes as we move from a small lab flask to a massive industrial tank. First, empirical models. It is based on historical experimental data, so we use past success and mathematical correlations like the one shown on this graph, so to estimate the best settings for the larger scale. Second, mechanistic models. It relies on the law of physics, so they use transport and kinetic principles to calculate exactly how oxygen and heat move at molecular level to ensuring the biological environment remains stable. Third, computational model. It creates a digital map of reactor by dividing the tank volume into thousands of small zones. A computer can track and simulate how nutrients and cell move throughout the entire system. Finally, CFD. So it is the most advanced tool. It uses 3D simulations to visualize fluid flow and shear stress. As you can see in the colorful map, it helps us to identify red zones or high pressure areas. So it allowing us to fix the design problems before we ever build the actual reactor. So when we discuss about industrial importance, it is not simply about increasing equipment size. It is about ensuring the process remains efficient, safe and profitable. First, it is to improve productivity. Successful scale up ensures that the high yields we achieve in the labs are maintained at an industrial scale. So this allows us to maximize the output of every liter in our large scale vessels. Second, it ensures consistent product quality. So in biopharmaceutical, safety is non-negotiable. Precise modeling guarantees a uniform environment throughout the tank. So meaning every batch of medicine is identical and safe for the consumer. Third, it reduces production costs. A single failed batch at an industrial level can result a loss of millions of dollars. So by using the models that I mentioned earlier, we get the process right for the first time. So it significantly reducing waste and energy consumption. Finally, it is essential for industrial success. Scale up is the bridge to commercialization. So it is the only way to mass produce life-saving products and make them affordable and available to the global market. So in short, scale up is the foundation of turning biotechnology into successful global industry.
This slide explains the common scale-up problems. When we move from a small reactor to a large one, several issues can appear. First is poor mixing. As the reactor gets bigger, mixing becomes less efficient and dead zones can form. This can cause incomplete reactions or lower yield. Second one is heat transfer limitations. Larger reactors have a lower surface area to volume ratio, so heat is harder to remove, which can lead to hotspot.
Next, we have mass transfer issues. Gas-liquid transfer like oxygen transfer decrease at larger scale, which can slow microbial growth. And the last one is shear stress differences. Bigger impeller may generate higher shear, which can damage sensitive cells and reduce productivity. These challenges can show why scaling up is never 100% straightforward.